All right, recording is rolling. Today is Wednesday, September 21st. And you guys, as the planners, we're going to be doing as many textbook problems as we can. Now this is actually it's from two chapters in your textbook. Chapter 4, forces in one dimension, and then chapter 5, forces in two dimensions. So trying to guys a few problems from each of those, all on one page right there. Okay, so before we get to that though, a few other things first. You guys remember this whole thing about you're going to get laptops from the school at some point, laptops from the school? Right, so there was a faculty meeting this morning, and news I have on that is Friday, October 28th is going to be laptop day. Supposedly this is gonna be like a whole day thing where they're gonna check out the laptops to you, and you need to like watch certain videos and sign certain agreements and blah, blah, blah. And I don't think you're really gonna be learning much or any content in your classes that day, including this one, just because the full focus is gonna be on anything to do with laptops. I don't really have any details beyond that because they need to tell all the teachers to exactly how that's gonna work, but that's what I know so far. So it's about 5 weeks from now. All right, so we got that lined up. The other thing I want to do before we start hitting textbook problems is last couple of days we've been doing free body diagrams, and gotta share my screen for the video here. Share screen to here we go. Okay. And we're actually at really close to the end of the presentation, so let's go ahead and knock out the rest of these. Okay. Also, some of the ones coming up are going to look like your lab tomorrow, so that'll get you guys a head start. So this is the last one you guys saw, block at rest on a ramp. Okay, there are three forces. Right, there's the weight down, the normal force up to the left, and a friction force holding in place up to the right. Okay, and then I told you guys for anytime you have an incline like this, to always introduce the Cartesian system parallel perpendicular to the surface. I see these very light dashed lines. Okay, and then to put all the forces in terms of those. Now the normal force is already aligned to that rotated system. It's called normal. Normal means perpendicular to the surface. So that one's already aligned. The friction force is always perpendicular to that force or parallel to the surface. So that one's already locked in place too along this axis. But you would need to take the weight and break it into those purple dashed components, right? And then think in terms of those components, right? So we're taking the one weight and thinking of it as if it's two components, right? And then from that point of view, can you guys see that the mg cosine theta and the normal force exactly balance out along this axis, right? So the normal force is equivalent to the cosine component of the weight, right? And then same story with the friction force. See how the friction force balances out with mg sine theta, right? So the friction force is equivalent magnitude to the sine component of the weight for as long as the block is in equilibrium, and at rest is one example of equilibrium, right? Right. So that's the last one you guys saw. Here's the next slide. What if the block is sliding down at constant velocity? Oh, guys, sliding at constant velocity. Is that an example of equilibrium? Yeah, it is. Because constant velocity, what's the acceleration? 0. So what's the net force? 0. Is that one going to have a free body diagram that looks pretty well exactly like the last slide? Yes, it will. So let's go ahead and put that in here. It has the weight. We're going to introduce Cartesian system, break the weight into components, normal force, friction force that balances out mg sine theta. That does look exactly like the last one. Okay. Now, if there's a slight technical difference, it's that this friction force is kinetic friction instead of static friction, right? Which might happen at a slightly different angle for, given the materials of whatever's blocking this surface is made out of, right? But if you were just given this free body diagram with no other context, you would not know if that block was at rest or sliding down at constant velocity, because it could be either one. Right, it'd be ambiguous. Okay, this green velocity vector is not actually part of the free body diagram, right? Free body diagram, you only care about force vectors, right? Let's do one more with the incline. Let's have it sliding up the incline. Now, this one actually will be different. What's the one difference for this free body diagram compared to the last couple of slides? Yeah.
Friction's in the other direction.
Boom! Friction's going to reverse direction, because doesn't friction always oppose the motion, right? All right, so let's go through the process. Has a weight. Let's introduce the Cartesian system. Bam, right there. Break the weight into components. Bam. Introduce normal force. Bam. And then, all right. So far it's all the same. Okay. But friction. Friction is going to oppose the motion. Now that block right there, is that block in equilibrium?
No.
You're right. It is not. Right. How do you know?
In the process of slowing down.
True. It is in the process of slowing down. Right. You guys see there's a net force on it. Right. Now the normal force and the mg cosine theta cancel out, or they balance out, so I'm not worried about it. But you guys see the friction force plus the mg sine theta? Those are conspiring together to create a net force down to the left, okay? Which means there's an acceleration down to the left. Newton's second law of motion, acceleration and net force, same direction, okay? Which is opposite of velocity, which means it's slowing down. Yeah. Like I said, that block's slowing down in a hurry, isn't it? Right? It's got it's got friction force and also the sine component of its weight, both saying, no, let's go the other way. Okay. So, all right. Atwood. All right, now this is what you guys are doing tomorrow. You guys remember yesterday I broke out this pulley. You guys had a red pulley, a couple lab weights, set some string, set this up for you guys. Okay, so this is what you guys are going to do tomorrow. Tomorrow you guys are going to investigate. If you swap out these masses M1 and M2, how does that affect the acceleration of the system? Say like looks like M2 is going to accelerate down and M1 is going to accelerate up, right? Counterclockwise, they're all tied together on the same string. And can you like piece together a formula, right? Now there's a couple ways to get to the answer. And I'll sort of set up with guys on this slide, one process that's going to lead to one way of solving this, right? And then tomorrow you guys are going to get empirical data and maybe get the answer like a different way, right? To get a different track through the force, right? So each of these blocks, each of these masses, I would say has a weight, right? That would be proportional to the mass. So if M2 is triple the mass of M1, it also has triple the weight, right? So we got that, right? In fact, those forces right there, just those weight forces, I'm sort of revealing, kind of leading you guys down the path of one way to think about this and solve this. Okay? Those are the only two external forces that's going to drive the masses to move. I'm sort of ignoring the fact that you're holding the pulley in place. But let's just say the pulley's fixed in place, and I'm just focused on the two masses, right? So those are external forces, right? The Earth is pulling on each of those masses, right? And there's kind of like a tug of war going on, right? M2 says, let's go counterclockwise, and M1 says, no, let's go clockwise, right? You guys see M2 is going to win, right? Right? But if you want to get more granular, look at like a micro point of view and hone in on each of those masses, isn't it true that there's also a tension force pulling up on each of those masses? Okay. But notice how I drew the tension force, right? A few details. One is that as long as this pulley is basically frictionless and massless itself, right? That string, a single string can only have how many tensions in it? One. Yeah, one string, one tension. If everybody plays tug of war against each other, that one rope only has one tension in it, right? Okay. So same story here. Again, as long as this pulley is basically frictionless, right? Which pretty close to. Right? Okay, so you guys see that it's the same tension force on each block, right? And now look at the magnitude compared to the weights. Do you guys see that M2 has a net force downward, but M1 has a net force upward? Ooh, look at that. Because that's going to drive M1 up and M2 down, isn't it? Doesn't each of those blocks accelerate the opposite direction? One's going up, one's going down. Okay. Do you think the magnitude of acceleration is going to be the same for both blocks? Yeah, has to be. I mean, they're tied together with the same string. They have the same motion, except one's going up, one's going down, right? Interesting, right? So they each have a net force. Okay, is that right? Now, if I want to do total overkill on this one, then I could also look at the pulley. So now there's like 3 free body diagrams, right? One for M1, one for M2, and then also like you're up here holding the pulley. Okay. Now, why could do this overkill thinking about the pulley help you out a little bit? Right? Because you might remember yesterday when I broke out those materials and I did a quick demo with you guys, I said, think about certain extremes, like certain boundary conditions of what you could do with those masses. This is a trick I picked up from engineering school. If you have a big complex problem and you're trying to wrap your mind around it, sometimes it helps to frame the problem by saying, well, what if I do like some minimum input and some maximum input? In this case, the two extremes could be, first of all, what if M1 and M2 are the same? What if they're the same mass? 1 kilogram, 1 kilogram, right? What's that system going to do? Just kind of hang out there, right? Not really move, right? Or if it is moving, just constant velocity. I guess that'd be technically possible. But then, do you guys think if this is 1 kilogram and this is 1 kilogram, they each have a weight of 10 newtons, 10 newtons, 10 newtons? And what do you think the tension in the string would be? Also 10 newtons, right? Got 10 down, 10 up, 10 newtons down, 10 newtons up, right? And the tension of the string is just 10 newtons, right? And how much force do you think you would need to hold the whole system up? Maybe 20 newtons, right? If the string is negligible mass and the pulley is also negligible mass, right? You need 20 newtons to hold it up. That'd be like twice the tension, right? That checks out. All right, let's go back to the boundary conditions framing of this problem, right? Because the other extreme thing you could do is you could put all the mass on one side and just leave an empty string hanging out on the other side, right? In that case, what would be the acceleration of that mass? Wouldn't it just be 100% of gravity? Just pure free fall, 10 meters per second squared, right? What would the tension in the string be? Zoop. Probably zero, right? Kind of check out, right? And how much force do you think you would need to hold this up as it's probably no force? Hey, and twice of zero tension it would in fact be like zero force to hold it up, right? As it's just free falling, just doing its own thing, right? Okay, so kind of got a way to frame that problem, right? Now tomorrow, I'm gonna have you guys calculate the acceleration using kinematic motion. You say, well, if this block's move a certain distance and a certain time, you guys are gonna bring your stopwatches tomorrow, right? And your cell phones, stopwatches, right? And it starts from rest. That's 3 kinematic values that you can calculate the acceleration. Okay, then you have some input values, each of the masses. Or if you can like make a formula of that to govern the motion, regardless of what the mass is. Right. Finally, modified Atwood. So if we have time to do this lab, I'd like to have you guys run this one too. So you can modify this by having just one of the masses driving the motion with its own weight, in this case, M1, right? And have the other mass moving horizontally. Now, a nice thing to do with M2 is to either have a frictionless tabletop, like an air hockey table, or to slip a Hot Wheels car under. Could you guys slip a Hot Wheels car underneath M2, right? It basically remove the friction, right? And do you guys think that there's a normal force holding that block up, right? Do you guys think that the weight of M2 and the normal force on M2 are balancing each other out? Yeah, right. And if I stop right here, then I have the macro point of view on, like, from a systems point of view, what's going on with the system. Do you guys see that there's only one force that's even driving the system to move? It's just the weight of the one that's hanging, right? Right. Now, if I go a little bit more granular, if I get a little bit deeper, there are also tension forces inside here, right? The tension force is slowing down M1, preventing it from doing pure free fall, right? And it's also pulling along M2. And same story as before as the regular outlet. It's the same tension in that string, right? But see, why does the tension not drive the system to move? Because the tension is just internal to the system. It's just holding everything together, right? It's this external force down here, M1G, that's actually driving the motion, right? All right, so that takes care of that PowerPoint. All right. Any questions so far? Okay, so let's switch back over here and knock out as many of these textbook problems as we can. All right, so starting chapter 4, forces in one dimension, and I did assign some of these to you guys. So yeah, I think probably a good thing to do is go ahead and solve these with you and maybe change some of the numbers as we go along, so get a little extra practice. All right, so 58. You toss a ball straight up into the air. And then 3 parts to this. Draw a free body diagram for the ball at 3 points in its motion, on the way up at the very top and on the way down. Okay, so start with that. 58 part A. 58 part A. Okay. So take a ball, throw it up into the air. Okay. So here's the ball while it's moving up. Okay. Here's the ball at the top of its path. Okay. And then maybe here's the ball like coming back down. I shouldn't have put that velocity but there because you get the way the force vectors, right? Or I don't know, maybe we'll see. Okay. Right, so the ball, when it's moving up, as it's moving up, here, the little animation. What's one force on this ball as it's moving up? Can you guys think of any forces on this ball?
Gravity.
Yeah, gravitational force. Its own weight. Right. So that's true. Right. I'll label that mg. Right. Mass times gravity field. I like to, if you want to label it F sub g. If you want to just spell out the word weight, and any of those could work. Okay. Are there any other forces on that ball? No, that's it. That's the entire free body diagram. Well, maybe you could say air drag if you like air drag, but if you ignore air, did it say anything about air drag? No. I guess it's open to interpretation. So yeah, that could be the whole thing, right? What about at the very top of its path? What forces?
No gravity, no velocity.
Okay, that's it. Just its weight. Right, and what about when it's headed on the way down? Same story. Right, now, if air resistance is negligible, or if it's in a vacuum, then doesn't each one of those snapshots have the exact same free body diagram? Sure does, doesn't it? Exact same free body diagram. That's it. Right. And tell you what, if you were to put in air drag, let's make this a little more complicated. Let's say there is air drag. Okay. So when the ball is moving up, which way does the air drag point? Like opposite of the motion, right? Like this way. I'll do F drag. Okay. At the very top, guys, if you throw the ball straight up, at the very top, the ball has 0 velocity. It's not even moving relative to the air, so there's definitely no air drag, is there? It's not even moving. Velocity 0. Right? And then when it's moving down, which way does air drag point? Opposite of the motion. Do F sub drag this way. Okay. Is that? Ooh, let me ask my own Griffin question. If the ball starts at the ground and also ends at the ground, and there is air drag, see if how much time would it take to go up compared to down? Does it take more time to go up or more time to come down? See, if there is no air drag, it's equal, right? If it takes 3 seconds to reach the peak, it also takes 3 seconds to fall. What about if there is air drag?
It's all the same both ways.
Well, it's gonna be one or the other.
Does it take longer for it to reach the top because there's more forces happening down?
There's a greater force downward, right? There's a greater net force, right? When it's moving up, right? Here, think about this. Isn't this ball here like slowing down in a hurry? Okay, so right, slows down in a hurry. But this ball here, in fact, if you do that engineering trick I told you guys to take things to extreme, maybe F drag, if it reaches terminal velocity, F drag might even reach equal to the weight, right? Isn't this ball just like taking its time, like la-di-da-di-da, just coming on down? Because there's a very small net force on this one. There's a huge net force on this one. So this ball is slowing down in a hurry, going up. This ball coming down, it's taking a long time to come down. I think it takes more time for the ball to fall back down. Right. So fun scenario. What does this say? Specify and identify the forces acting on the ball and their agents. Okay, so the weight would be, you can call that a field force caused by the earth, right? The earth is pulling on the ball. And then this drag force, might call it contact force. The ball against the air, right? I don't make a big deal about field forces and contact forces, but I don't know, some textbooks do, so you see that someday. Right. What is the velocity of the ball at the very top of the motion? What's that? 0 velocity. Velocity at the top equals v sub top equals 0 meters per second. Right, that's part B. And part C, what is the acceleration of the ball? Also at the top.
9.8 meters squared downward.
There you go. So, yeah, G downward. If you want to specify a number like 9.8 or 10 meters per second squared, downward. That's true. Okay. Hey, what about when the ball is moving up or moving down? Now, if you ignore air drag, of course, it's G downward all the time. Right? But what if you include air drag? Is the overall acceleration of the ball moving upwards? Would it be closer to 8 or closer to 12 meters per second squared? 12 downward, because both forces are acting way. What about this one? Maybe closer to 8 meters per second squared, because these two are subtracting from each other, right? And it could go all the way to 0 if it's terminal velocity, just right, 0 acceleration. All right, you guys carry on 58. 69. Assume that a scale is in an elevator on Earth. I like this question a lot. In fact, I made a new poster for you guys, but you put that together and put it on my ceiling. It's not up yet, but I was working on this last night. What force would the scale exert on a 53 kilogram person standing in it in the following situations? Okay, and then we got all these different scenarios. The elevator moves up at constant speed. The elevator slows at 2 meters per second squared while moving upward. It speeds up 2 meters per second squared while moving downward. The elevator moves down at constant speed, or it slows to a stop while moving downward at a constant acceleration. Woo! All right, so a lot of different things we're going to do with the elevator. So here's what I do with this. give you guys some notes, give you guys a big picture point of view of what's going on with the elevator, and we'll go through and tackle those questions one by one. Okay. So, break out a little for this. Marble alert, elevator have straight lines. It's got a wonky elevator, that'd be pretty sketchy. Not getting a wonky elevator. So here's an elevator. Okay, it's got like a center of mass. Okay, here. They talk about a person standing on a scale. Let me do this. I'll draw a person standing on a bathroom scale over here, right? And it's gonna be the same physics as, I'm gonna modify the situation a little bit, right? I'm gonna look at the tension in an elevator cable. Okay, I'm gonna do T for tension. Okay, so T equals tension. Okay. Sometimes we'll do F sub T because capital T sometimes stands for time period, but in this case, it's just gonna be tension, okay? Okay, tension elevator cable. And this elevator might also have a weight acting down. Okay, and I'll call that mg for the weight of the elevator, right? Okay. Mass of the elevator times the free fall gravity. Okay, so okay, the elevator has some weight, like some number of newtons. Okay, there's a tension in the elevator cable. Okay, now this is analogous to if you're standing on a scale. This guy right here has some weight, and there's a normal force from the scale pushing up, holding him in place. That be true? Okay. Now, if I had a bathroom scale in this room, you step on the scale, wouldn't your weight down and the normal force up be balanced out, so be the same? Right? So the scale is just going to read your weight. Okay. But what if you take that scale inside an elevator and the elevator starts accelerating? Do you think that scale is going to change the reading? Yeah, because the scale is really telling you the normal force. That's really what it's saying, right? If you're in an accelerating environment, then well, if you're accelerating up, I bet it's going to read higher than your usual weight. If you're accelerating down, like closer to free fall, I bet it's going to show you being a little bit lighter than you normally are, right? That makes sense? Right. Right. So let me do. Let's go back to the story that I have set up, which is like the tension in the elevator cable. It's like the same story, just it's the same math. Okay. Now, what if we had something like this? What if the elevator is moving up at constant velocity? Guys, if it's a constant velocity, what's the net force on it? Yeah, so the net force would be 0, right? So wouldn't the tension be exactly equal to the weight as long as it's moving up constant velocity? Also, if it's moving constant velocity, let's go to this guy standing on the scale. Suppose this guy weighs 500 newtons just at rest, like out here in this room, weighs 500 newtons. Right? If he's standing on a scale in an elevator, moving up at constant velocity, does the scale still read 500 newtons? Yeah, still reads 500 newtons because constant velocity. Remember, you guys remember from a physics point of view, constant velocity is indistinguishable from being at rest. You guys remember that? They're both equilibrium, right? So I'd have to draw this elevator tension as being like equal to the weight. That's why I'm covering up the top part of it here, right? Okay. You guys remember if you're in a car going cruise control of I-95, you can't tell how fast the car is going, right? As long as you're going constant velocity. Okay. Okay. So let's go to my drawing here. You guys see how I drew the elevator tension as greater than the weight, right? That's an indication that the elevator is doing what? Is this elevator as I've drawn it accelerating? Yes, it's accelerating up because there's a net force upward, right? The tension is greater than the weight. So there's a net force and it's going to accelerate upward. Two ways to accelerate upward, right? Maybe the most obvious way. Oh yeah, you guys remember this? We talked about this already. Here. You guys remember doing this in the spring scale lab? Right? You guys did this one, right? And then this is a modified version of that. Yeah. Yeah, here, got a extra copy of this here. So the most obvious way is you could have the elevator moving up faster, faster, faster. But what's the other way to also accelerate upward? Can the elevator move down and accelerate upward? If it's doing what? Slowing down. Moving down, slowing down could also be this free body diagram, couldn't it? Okay. And that would also make this guy look like he weighs more than he normally does. Either moving up, accelerating up, or moving down, slowing down. Either way, this guy's going, oh, I'm super heavy for both of those situations. Okay? They're physically identical from a forces point of view. All right, so here's what we do. I'm going to set up Newton's second, or hold on, no, let's do this. Let's say the net force, F net. Okay, is the difference between the tension pulling up and the weight acting down, right? So the tension minus the weight, here, maybe I'll spell it. So the sum of the forces is tension minus the weight. There you go. That step to lead to that step, right? That's right. Now, net force. You guys remember from Newton's second law of motion, net force is mass times acceleration, right? If you put a net force on something, you put net force on a mass, they'll cause it to accelerate, right? Okay, so I'm gonna take advantage of Newton's second law of motion and substitute that right here. Okay, so sum of forces, net force, same idea. Okay. This is mass times acceleration for the elevator. Okay. And that is, again, tension in the elevator cable minus the weight of the elevator, right? Like the gravity force of the on the elevator, right? Okay, now what I'm gonna do is rearrange this, and I'm gonna solve for what is the tension in the elevator cable. Okay, tension in elevator cable. It's the tension I'm talking about, right? I do a little algebra switcheroo and get tension is equal to just the usual weight of the elevator plus mass times acceleration of the elevator. Is that true? I guess that. In fact, if the elevator has 0 acceleration, then wouldn't the tension just be equal to the weight of the elevator just to hold it up? Okay. And then the analogous story, the normal force reading on the sky would also be his just regular weight, right? Okay. So that might be at rest, or again, that might be moving at constant velocity, either up or down. If you're moving constant velocity, you can't tell the difference from being at rest. Right? Okay. And I'm gonna throw in another step here. Yeah, that's the same M, isn't it? Mass of the elevator, or for this guy, mass of the guy, mass of the guy. So I'm gonna factor that out because basically the tension then is gonna be mass times, and then you could like sort of like change the acceleration, right? There's gravity like plus the amount that's actually accelerating. Right. All right. So now this is for as long as the elevator is accelerating up. So let's say if accelerating upward. That's true. Okay. Now I could go back, break out another piece of paper, do this whole thing from scratch for the opposite case. What if I do this? What if I made this tension really tiny compared to the weight? Okay. Or at an extreme, all the way to 0, you cut the cable, start accelerating down. In that case, well, there'll be something to do with the elevator accelerating downward if the tension is very small compared to the weight, right? And I bet this guy would feel like a partial free fall, so very light for that situation, stay on that scale. Okay. So I'm going to generalize this by saying this: tension in the elevator cable is M times, and the only difference is this plus would change to a minus, right? If you want to try that yourself, you can see that's going to be the case. G plus or minus A. Okay. This is a nice handy formula to hold on to in your back pocket. Right? If you ever want to know what is the tension in an elevator cable based on its acceleration, right? Then here, I just derived this whole process for you guys. And if the elevator is accelerating up, you add that acceleration to G, right? If, for example, if it's accelerating up at 3 meters per second squared, you 10 plus 3, and then multiply by the mass of the elevator, get the tension in the elevator cable. But the one I boxed in down here could also handle if the elevator is accelerating downward, closer to free fall. If it's accelerating down at 3 meters per second squared, you do 10 minus 3, and then multiply by mass to get the tension, right? Which would be less than to hold it, right? Okay. How about this? Let's test this a little bit. See if this is really true. What if I cut the cable? And this is in pure free fall. Down at 10 meters per second squared. Would that be accelerating down 10 meters per second squared? Could you do G minus G? That would be 0. 0 times mass, that would be 0 tension. Which of course it would, because cut the cable. Right. Got that? Okay. And then to change it from the story of the tension in the elevator cable to this guy standing on the scale, the only change is, well, instead of mass of the elevator, it's mass of the person. And instead of tension, now it's the normal force reading from the scale, right? So maybe this guy has his own free body diagram. I've got my own weight, mass of the person times gravity. And I've got a normal force reading from the scale, F sub n. Right? If I replace this T tension with normal force reading, then it tells the same story for the guy. Right, is it? All right, so, questions so far? Does that kind of check out, kind of make sense?
What is what is NA stand for again?
Mass times acceleration.
Oh.
Yeah, which is caused by some net force. Yeah, it's Newton's second law of motion. Mass times acceleration. Okay. All right, so with all that in mind, they gave you guys a whole list of questions here involving what motion of this elevator. Is that what's going on? Let's go through these one by one. Say the elevator moves up at constant speed. Guys, constant speed. What's the acceleration? 0. So isn't the tension in the cable just going to be m times g because a goes to 0, mg, and this guy's scale rating is just his usual weight, just mg. Everything's just mg, right? I check out. The elevator slows at 2 meters per second squared while moving upward. Right now, guys, if it's moving upward and slowing down, then should I have this free body diagram or should I have a very small tension? Yeah, very small tension. And the tension should be less than the weight because it's accelerating down, right? And if you navigate this formula, do you want to do a plus or a minus here? Yeah. Oh, yeah, you got it. Yeah. I'm thinking minus, right? Because we're putting a little slack in the table, right? Or this guy feels on the scale feels a little bit lighter than he usually does. Okay. Here, let's pop up some numbers here. So I'm going to use. Well, they gave you the mass of a person standing on the scale. Let me say mass of an elevator, just to change it up a little bit. Let's go 1,400 kilograms. Just make something crazy up. 1,400 kilograms. Okay. All right. So part A, the elevator moves up at constant speed. What's the tension in the elevator cable? Tension would just be mg plus or minus a, which goes to 0. Tension is equal to mg. Take my 1,400 kilogram elevator, 10 meters per second squared. I'm getting 14,000 newtons. That's part A.
Okay, wait, is it asking for? Oh, it is asking for the force. So the tension is the force exerted on the person.
Okay, so we got 2 different stories here. Yeah, your textbook is asking about the normal force rating on the person, right? In the notes, I'm giving you guys tension in the elevator cable, but it's the exact same math, the exact same physics, right? So the only difference is instead of tension, you just say the normal force rating, okay? And instead of the mass of the elevator is the mass of the person, right? So standing on the scale, right? See if the elevator is accelerating upward, the only way for that to happen is if there's a huge tension in the cable. Huge tension greater than the weight is going to cause the elevator to accelerate upward, right? Which is going to push the floor up into this person really hard, which is going to make this guy feel really heavy. And the elevator, the scale is going to show that this guy weighs more than he normally does. Okay. So all of goes hand in hand. It's all proportionally the same. Okay. Yeah. Okay. Part B, suppose you're slowing down 2 meters per second squared while moving upward. So for the notes, I'm doing tension in the elevator cable, but you guys can do the normal force rating on the guy, the scale rating. Same math. Okay. Right. It's still going to be m times g minus a because you're accelerating downward. Now you have to figure out that it's minus, not plus, because accelerating downward. Okay. So I'm going to take my 1,400 kilogram elevator. And I know that usual Earth gravity is 10 meters per second squared, but I'm accelerating downward at 2 meters per second squared. That's like, ooh, it's not like 8 meters per second squared. Right. So now I have oops. The tension is only this many newtons, okay? Which is less than it was before, right? If it's just holding the elevator at rest or constant velocity, then it's this number. But if it's accelerating down, right, then no, it's less. Okay? In fact, if you're thinking like cause and effect, really it's cause and effect the opposite way. By having a smaller tension in the elevator cable, it allows it to accelerate downward. Okay. And then part C, it speeds up at 2 meters per second squared while moving downward. Guys, if you're speeding up downward, that's accelerating which way? Up or down? Down. Isn't that physically identical to what we just did? This is part B and C. That takes care of both of them, right? Because if you're moving up, slowing down, or if you're moving down, speeding up, right? Yeah. Part D moves downward at constant speed. Hey, downward at constant speed. Is that a case of equilibrium? Is that the same as being at rest? Or the same as moving upward at constant velocity? So part A and D are identical. A and D are identical. B and C are the same as each other. A and D are the same as each other.
When you say the same, like, you mean the same formulas or the same numbers?
Both, yeah, exact same,
Wait.
exact same outcomes. Yeah, okay.
So the. Wait, so how would that work for the person? Because. If the elevator is moving up, he's experiencing more force. So he feels heavier, but when the elevator is moving down at a constant speed,
Huh?
how does that make him feel heavier?
Okay, so remember, it's not which direction the elevator is moving, it's not about velocity, it's about acceleration. Okay, so if you are moving up but slowing down, then you'll actually feel lighter than you normally would. Okay. Which would also be true if you're moving down faster and faster, right? In fact, if you're this guy standing in an elevator, okay, let's say this guy knows he weighs like 500 newtons. It's like, okay, or actually, you know what? I'll do your numbers, because all you guys have to do, different from my notes, is just pop in 53 kilograms for mass. Okay, I said 1400 kilogram elevator. You say 53 kilograms for the guy, right? And then everything else, right, follows. Okay. The tens there is still two, so there. Okay. So your guy should usually weigh 530 newtons. That's your answer to part A. You guys got 530 newtons. That's what you guys got, right?
Oh, I got a way different number.
You guys did 53 times 10, right? For part A. The mass of your guy is only 53 kilograms, right? Okay. And then, so your guy weighs 530 newtons, right? If he's just sitting at rest in the elevator, the scale reading would be 530 newtons. If the elevator moves up at constant velocity, it's still 530 newtons. If the elevator moves down at constant velocity, it's still 530 newtons. In all those situations, the scale reading is the same, it's just 530 newtons, right? But suppose he looks down at the scale reading, and says, whoa, I feel kind of weird. He looks down at the scale reading and it's showing like 400 newtons. Like, whoa, looks like I lost a lot of weight, right? One of two things has happened. Either the elevator is moving down faster and faster, like he's in partial free fall. Maybe he started at top floor, and the elevator starts to move down, it's accelerating down, right? Or what's the other thing that could be happening? The elevator might be moving up and doing what? Slowing to a stop. That could also produce the exact same effect. Okay? And that answers both B and C, right? So part B was moving up, slowing to a stop, and part C was moving down faster and faster, but those are physically identical and they'll produce the same number. Now for you guys, that'd be 53 kilograms times 8 meters per second squared, because 10 minus 2 is still 8. Okay. You guys got that? All right. And then one more part to this. It slows to a stop while moving downward with a constant acceleration. Let's tag a number to that. Let's say 2 meters per second squared. Because if you're moving downward and slowing to a stop, which way is the acceleration? Up or down? Up. Yeah. Right. In fact, wouldn't that exactly match this free body diagram? Right. Where there's a greater upward force than downward force, or for the sky on a scale, greater normal force than weight. Right? Is that true? Okay. Which we do have to do a separate calculation for. So part E, I'm going to go the tension in my elevator cable, but you guys can say the normal force rating on the scale is equal to the mass. For me, it's the elevator. For you guys, it's the guy. Okay, and do G plus A. Okay, so if I got 1400 kilogram elevator, let's say 10 meters per second squared. Let's have this acceleration be the same value, just opposite direction that's moving forward. Let's go 2 meters per second squared. Let's say that's the rate that the elevator is slowing as it's coming to a stop. Let's move down. Okay. So 10 plus 2, oh, that's 12. I'm getting this many newtons right here. Right. Of course, your guys' numbers are different than mine, but it's the same setup. You do m times g plus a. Okay. Where the m goes, put 53 kilograms. Where the g goes, put 10 meters per second squared. And for the a, well, they didn't actually specify, but I'm just using 2 meters per second squared. Okay. And do you guys see that's the largest force value on this entire page, right? So whether you're moving down slow into a stop, or if you're moving upward faster, 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 either one of those, it's going to require more force to do that. Okay. Okay. Guys see that? All right, so that was a fun adventure in that elevator. All right. Okay. I did assign you guys a 60 and 64. Those are kind of hidden out here in the middle. So oops, let's go hit those. Actually, these are a bit more straightforward. Number 60, skating. We got Joyce and Efwa, or I think, are skating. Joyce pushes Efwa, whose mass is 40 kilograms with a force of 5 newtons. What is Efwa's resulting acceleration? This one, I think you can get different answers based on interpretation, but I'm going to do the simple version of this, which is suppose I'm going to have Joyce just standing on ground, so I'll do J for Joyce, right? And Efwa, I'm going to actually put on skates, your roller skates here. Okay. So there's Efwa, right? Guess that. Okay. Now, why did I only give Efwa skates? So that when Joyce pushes her, Joyce stays in place, and that the only person that accelerates is Efwa. Like Efwa gets the full force, right? Guys, this is just going to be Newton's second law of motion. The acceleration that's caused is the net force divided by the mass. Isn't that it? Right. Now, if I did a free body diagram on Efwa, I'm thinking of 3 forces. There's the weight down, there's the normal force up. For those two are just going to balance out, right? And then there's the pushing force, and that's the one I care about, because the pushing force is going to be the net force, isn't it? Right. So let me change the numbers a little bit so you guys get a little more practice. Suppose Joyce on my paper pushes with like 15 newtons, 15 Newton force, okay. And my F was gonna weigh a little bit more. Let's say like 45 newtons, or sorry, kilograms, 45 kilograms, okay, something like that. So net force divided by mass. Won't that result in some acceleration? And this looks like it's going to be, I think I can do that in my head, meters per second squared. Okay. Is that true? Okay. Now that's just while the push is happening, right? That's only during the push. Right? What about when they break contact and F1 starts like flying off, right? Starts rolling off? What is the what's the acceleration of F1 after the push happens? Yeah, 0. Yeah. Now she's just coasting. It's going. Is that true? Okay. Okay. Ooh, you know what? I'm gonna have my own Griffin question here. Suppose that the length of the time the push happens for, I'll say delta t, like, or let's just say t. Okay. Let's say the time of the push is like a half a second, 0.50 seconds. Okay. Can anybody tell me how fast F was going to be going after that time? Oh, let's use my numbers, right? So let's just use the numbers on this page. Okay. If you tell me how fast, and I don't know the answer yet, so let's see. I'll get it while you guys get it. All right, I got the answer. We figured it out. How fast is F1 going at the end of that push? Everybody got it? Are we going to kick back to these 3 amigos right here? Say, if I told you the time interval of the push and F1 started from rest, and you know the acceleration, because we just calculated it, hey, that's 3 kinematic values. Right, start from rest to 0, so that just goes away anyway. Is it just a times t? Just that times that? Okay. I did that and got like that many meters per second. Right. So go the velocity you build up to here. I'll do the whole thing. You're not plus at. Right. This is just 0 meters per second, starting from rest. This time, right there, this acceleration, right there. And the roll away speed is this many meters per second, if that was a question. Okay. That's a cool thing you can do with dynamics is if you know the force and you know the mass, you can calculate the acceleration. And see how acceleration is kind of a bridge between last unit and this unit, right? This is what we did before. You know, it's kinematic stuff going on. I don't say anything about forces, although there had to be force cause of acceleration. Okay. But acceleration is like the bridge between kinematic motion that you're seeing right here in this dynamics, which is like Newton's laws of motion. Okay, they both involve acceleration. Like that. Go back and forth between them. Let's take a look at 64 motorcycle. Your new motorcycle weighs that many newtons. What is the mass in kilograms? Okay. So you guys remember how I've been writing weight? Weight equals, how have I been labeling those free body diagram forces with weight? mg, right? Which is two variables multiplied together. It's mass times gravity field, isn't it? Right. So if you knew two of these things, couldn't you solve for the third? So they told you the weight in newtons. So suppose I have a motorcycle that weighs 2,000 newtons even, 2,000 newtons. Okay. And I know I'm on Earth, so probably it's about 10 meters per second squared. What's the mass of my motorcycle? 200 kilograms. Is that just divide over? Right. Newtons over meter per second squared gives you kilograms. So the mass of my motorcycle is 200 kilograms. Okay. And for you guys, that's kind of close to that. It's a little bit different. Right? You guys can do that? All right. And this next one lined up here looks exactly like what you guys are going to be doing tomorrow, or pretty close to. They also asked about the tension. So we're going to have to save that one for another day to got an Atwood going on. All right, you guys have a great rest of your day. Atwood tomorrow.